iterations or whatever, it's going to converge to a point. So, a couple things to notice, right? X sub 1 is equal to px, or the probability vector, or the probability matrix, sorry, times the initial state vector. So this implies that x sub n is equal to the probability matrix times the state vector n minus 1. Also, if you notice, x2 is going to equal x, or probability of x is 1, right? And so this is going to be equal to p times p x sub 0. And so you end up with x2 is going to equal to p squared x 0, right? And more generally, if you look at it, you're going to end up with xn is going to be equal to the probability matrix to the nth power times the initial state vector, and that's going to be how you find any number of iterations, right? It's the number of iterations. And so if you take it and you raise it to whatever power, you want to know how many iterations and multiply it by the initial state vector, and you'll get the probabilities for the actual numbers, right? Because you can actually use probabilities instead of these initial these numbers right here, right, the initial state. So if you wanted to change this to x0 is equal to 110 over 200. It's not really a probability, it's a ratio, sorry about that. And 90 over 200, it's going to, that breaks down as a fraction to 0.55, or 55% and 45%. Right, so then you want to find x1, you just multiply it by the transition matrix here, and then you multiply your probability here, 55 and 45, and just without doing that, or without using a calculator or anything, or whatever, 0.475 and 0.525, right? And this is actually equivalent to, if you check, it's 95 over 200 and 105 over 200, right? And these are the same numbers we got. The 95 and the 105 are the same numbers we got for the actual total number of people that are doing the thing. So you can actually do it with percentage of people, so the initial state doesn't matter, and then you can just do the probabilities instead. And p to the n, the ij, the ijth entry of p to the n is actually the probability of going from I to j after n transitions. Right, so this just kind of makes sense that ijth column right here is going to give you the probability matrix raised to the n power is going to tell you your chance of going there. That's pretty nifty. Anyway, so finding the steady state, right? This we're actually going to have to use some eigenvalues. And the fact that there's an eigenvalue of 1. So anyway, so find the eigenvalue, right? You're going to need all the eigenvalues, sorry. Determinant of the transition matrix minus lambda I, and you get 0.7 minus lambda, 0.2, 0.3, and 0.8 minus lambda, right? And and so then, when you do that, it breaks down to lambda squared minus 1.5 lambda plus 0.05, which is equivalent to lambda minus 1, right? You got to always have this because the eigenvalue is always 1, so you know that lambda minus 1 is always going to be a factor here. And then lambda minus 0.5. So your eigenvalues here are going to be 1, which we expected, right? And then 0.5 is the other one. So that's good. So now we have to find the actual eigenvectors. And so to do that, you just take your probability matrix and you're going to subtract the lambda I, right? And then you get 0.2, negative 0.2, and then you have this as your eigenvector, right? Equals 0, 0. And if you just look real quick, it's going to be 2, 3 is going to be your eigenvector here. And so this is for lambda equals 1. So this is going to be the eigenvector that actually ends on your steady state. This is going to be the most important one. And then you also have your other eigenvalue, right? So you subtract 0.5 and you get 0.2, 0.2, 0.3, 0.3. And eigenvalue for this one's not bad at all. It's just going to be 1, -1. Right? It's pretty easy to see that this is these are linearly dependent because they're both just multiples of 1. So you get 1 and -1. Okay, so now that you've done that, you have to actually diagonalize the matrix so that you can find your infinite number of powers, right? Because you're going to have to raise this. Basically, you're going to take the limit as the thing goes to infinity to find your steady state. Now, obviously, you're not going to have like an infinite number of iterations, but there's a certain number of iterations where the probability just kind of converges anyway to your actual one. But as it goes to infinity, it absolutely converges. So first thing you're going to do, you have your Q matrix, right, of your two eigenvectors. It's 2, 1, 3, and then -1. Using the eigenvectors of the column. And you know that Q minus 1 times probability matrix Q is going to give you your matrix of your matrix of with your eigenvectors in there, right? It equals 1, 0, 0, and then 0.5. So simply put, you can do this. P to the k is going to equal Q times your matrix right here times Q inverse to the k. And if you multiply all this out, what you end up getting is like a Q d Q inverse times Q d Q inverse, on and on down the chain, right? And this is going to all these middle terms are going to cancel, so you're just left with a Q, a d to the kth power, right? Because the d's aren't going to cancel, and then a Q inverse. So this is pretty much how you do you diagonalize the matrix, right, of this right there, and then this is easy to compute because it's basically just going to be to the k and to the k whenever you take the limit. So if you take the limit of this, right, as k goes to infinity, that's terrible 8, but okay. So like if you take the limit as k goes to infinity, right, this term's just going to die. Like we saw earlier, that's just going to go away. So you're left with out of infinity, you're left with d is going to be equal to 1, 0, 0, 0. And so next thing you're going to do here is you're going to want to, so p to the k, right, is going to equal 2, 1, 3, -1 times 1, 0, 0, 0 times 2, 1, 3, -1, the inverse matrix here, right? And so once you do that, you're going to be left with equal to matrix 0.4, 0.4, 0.6, 0.6. And so then we just have to go back in, and we're going to x to the k, the x, the kth state vector, right? X k is going to be equal to p to the k times the initial state vector, right? Well, p to the k down there we just figured out was 0.4, 0.4, 0.6, 0.6. So you do, as k approaches infinity, you're going to end up with 0.4, 0.4, 0.6, 0.6. And we're just going to use an arbitrary state vector here, right, AB, so it doesn't matter what the initial state is. And so we're going to get is equal to 0.4a plus 0.4b, 0.6a plus 0.6b. And if you're dealing with probabilities here, right, we're just going to go ahead and start doing probabilities because you can convert the probabilities back to the initial state or whatever, or to your actual whole numbers. Sorry, you're going to with 0.4 and 0.6. So there you go. And it works for any x sub 0, right? It doesn't matter what the initial state is, whatever percentage of where is where, it's always going to end up being 0.4 and 0.6 when it gets off to really large numbers. And actually it doesn't take all that long to converge. 10, 15 iterations might be enough to actually get to that number, where it's like 0.4 and then a bunch of zeros and maybe 1 or something, but whatever, that doesn't really matter that much.